A student is given a standard galvanic cell. Again, this word standard means that the solutions are 1 molar. It's a 298K. That has a Cu electrode and a tin electrode. As current flows through the cell, it determines that the Cu electrode increases in mass and the tin electrode decreases in mass. Then it says identify the electrode at which oxidation is occurring, and that's fairly easy because um, if tin is losing mass, it's because the tin solid is turning into tin solution. And then you can see that the charge is going from 0 up to 2. It's not reducing. And uh, so something like this, explain your reasoning. Um, Identify the electrode at which oxidation is occurring. Oxidation is occurring um, at the tin electrode, because you always got to answer the question first. And this is bad. This should probably be a capital O. And then when it says explain your answer, that's when they want you to say something like, oh, tin metal is um, tin metal tin metal is forming um, tin ions in solution. Just say this: tin metal is forming tin ions in solution, um, so the mass is dropping, or something like that, or the mass is decreasing. Maybe that'd be better. So basically, identify the electrode at which oxidation is occurring. Oxidation is occurring at the, I'm an idiot, tin electrode. Um, just explain your reasoning. Tin metal is forming tin ions, so the mass is decreasing. Okay, so then as the mass of tin electrode decreases, where does the mass go? The atoms on the surface of the tin electrode are going into solution, or they're dissolving, however you want to say that. Okay, this is not bad. Very quickly, I had a hard time figuring it out this year, but if you look at the original picture, this is the top view. So it's like this is the top of the U. So copper is over here. Copper and copper plus 2 are over here. And then tin and tin plus 2 are here. And so we know that this is oxidation, so the tin metal mass is decreasing, but the concentration of tin is increasing. Vice versa, the mass of the copper metal is increasing, and because that's increasing, the concentration of the copper in solution is decreasing. And so basically, this half cell has an excess of positive charge, so the NO3 would migrate this way. And this cell has too little positive charge, and so then the K plus would go this way. And so that's really all that they wanted to see. Um, Okay, a non-standard cell is made by replacing the 1 molar solutions in the standard cell with 0.5 molar solutions. The volumes of the solutions in the standard cell are identical to those in the standard cell, or non-standard. So the volumes of solution in the non-standard cell are identical. Is the cell potential of the non-standard cell greater than, less than, or equal to the cell potential of the standard cell? And so just to answer the question, equal to. Um, Why? Because E equals E naught minus 0.0257 over N ln Q. Let's just talk about ln Q. ln Q is ln of the so of the tin concentration over the copper concentration. And when these are both 1, 1 divided by 1 is 1, and the natural log of 1 is 0. And the crazy part is when these are both 0.5, it's still zero point 0.5 divided by 0.5 is 1, which this term drops out. But because um, both of these, the ln of q is equal to 0, that's why it's equal to. Okay, so I didn't do a great job writing that down, so let me just grab an eraser. No, not that. I want to grab the eraser. Um, let's get the big giant eraser. So let me just say something like, so if you say this nice, you would say something like, sorry, I would say the cell potential of the non-standard cell is equal to the cell potential of the standard cell. And then here's a ln of q equals ln of 1 over 1 is the same thing as the ln of 0.5 over 0.5. All right, cool. Both the standard cell and non-standard cell can be used to power an electronic device. Would the non-standard cell power the electronic device for the same time, a longer time, or a shorter time? So even though they have the same voltage in the beginning, the non-standard cell would power the device for a shorter time as compared to the standard cell. And the reason for that is, if we go back to this slide, eventually this is going to drop to 0. What stops the battery operating is that eventually this goes to 0, and then everything stops. And so what happens is, to understand this question right here, because a 1 molar solution, remember how it said the volumes are equal? A 1 molar solution has twice as many copper plus 2 ions as a 0.5 molar solution, given that the volumes are the same. And so the 0.5, the non-standard cell, the copper plus 2 will be used up for faster. So the non-standard cell has a concentration of 0.5 molar Cu plus 2, whereas standard cell has a concentration of 1 molar. So Cu plus 2 would be used up quicker, I would say, because they're interested in the time. So the would be used up more quickly, let's just say. All right. All right, this page, using the information, and this doesn't look like yours, but it's hard to get it into this program. So basically, this question is, and um, now this is a totally different question. So, because it says, I'm going to sneak up and down. What it says here is that up at the top, um, oh no, I'm sorry. I think I did this wrong. But anyways, use the information above. Write a net ionic equation for the reaction between the tin electrode and the CuNO3 solution that would be thermodynamically favored. So this problem, I think my thing is not right here, but this is a different problem in that the tin electrode, this is not a battery. The tin electrode is hitting the copper nitrate solution directly. It's and so what happens is this is like last year, chapter 4. You have tin hitting copper 2 nitrate. And then what happens is that tin comes in and says, hey, copper, I'm going to kick you out. And you get tin 2 nitrate plus copper. And so then this equation is tin plus CuNO3 goes to SnNO3 plus Cu, and that happens to be balanced. And so you get this same kind of equation where this dissociates into copper 2 and 2 nitrates, and then this dissociates into tin and 2 nitrates, and then copper. But then with that spectator ion stuff, that's gone and that's gone. And what happens then is you end up with, sorry, this plus 2 is not here. You end up with tin metal and copper 2 ions turning into tin ions and copper metal. And what happens, sorry, that's a U, it looks like the tin has oxidized because the charge is going up, and the copper has reduced because the charge is going down. We got 0 and 2 and 2 and 0. And so when I hit extend this page quickly, and I got to go up and down, if you look, tin oxidized is, so I got to take that tin oxidized equation, which is the last one, and flip it around. And so tin flipped around so that it's, because on the sheet it's oxidized, this would be positive 0.14 volts. And then this is the second one on the sheet, so 0.34 volts. And then when you add them together, you get 48 volts. Now remember, 0.48 volts. They don't give you that big sheet that you guys have been using anymore. Everything they need will be provided. So if you come up here, this is, we wrote it down there backwards of this. So this gets flipped, and so this gets flipped, but then this is how we wrote it. So it's 0.34 plus 0.14. And by the way, that is thermodynamically favored because E is positive. And then this last question. Okay, why are you being this way? Hold on, I gotta grab this maybe. I do this last question. Okay, well, I think it asks for G. So then maybe I can go here. All right, no clue why I can't. And then they asked for G, and so G is going to be G naught is going to be negative NF E naught. And so you can see that it's negative 2 moles of electrons times 96,485 coulombs per mole of electrons times 0.48, but a volt is a joule per coulomb, and then 1,000 joules is a kilojoule. And so we end up with, again, I got to grab extend page. And it looks like because of this, we only get 2 sig figs. So negative 93 kilojoules, or remember they play fast and loose, or negative 93 kilojoules per mole Rxn. And remember, when delta G is negative, it's spontaneous. When delta E is positive, it's spontaneous.